Hi, welcome everyone to this session once again. So today we will discuss a very important topic on linear versus nonlinear analysis in StaAd. And one of the most important thing that you need to take into account while you are performing the nonlinear analysis. And that is the repeat load while you are combining the individual loading effect and you are doing some combined effect analysis. Now, first of all, before I dive into this load combination and repeat load, we need to understand what exactly is linear and nonlinear analysis. Now, to explain it in a most simplified way, I will just write this expression so that you can easily understand what we are into. So, for example, there is a function, individual function called fa, and there is another function which is called fb. Okay, now if fa and fb, if they are added together, if you are getting the similar effect where both A and B are acting together, if this left hand side is equal to the right hand side, then we can call it's a linear behavior. So it sounds very complex, right? But yes, so let's put it in a very simpler way. Now, for example, uh, this is a response call which is denoted by this function f. This is also a response denoted by this function f. So if I put input of A, and also here, if I put an input of B, I'll get some response, individual response against this one, right? If I combine them individually, I'll get some value, right? Now let's store this value somewhere. And in another case, we are getting a response when both A and B are acting together as an input. Okay, here A and B was acting individually, not together in separate situation. We have just algebraically summed them up. But here A and B are acting together. And this is the response that we are getting from this. Now, if we compare the numerical value of this one with the numerical value of this algebraic summation, if we are getting the same result, then we can say that the system is behaving linearly. And if this one is not same as the right hand side one, then we can say it is a non-linear system. Okay, now from the structural perspective, how does it come into the picture? So just put it like this. Let A be a loading input, B is a loading input, whatever inside the bracket is a loading input, and the result of this one, this function, is the, say, for example, response like forces, reactions, or displacement. Okay, so if from the structural perspective, if you're applying a load A and getting a displacement from this expression, then again in another instance in the same structure, if you're applying the load B and getting the displacement this, then if it is nonlinear if both A and B are acting together at the same point and you're not getting the same displacement. Okay, so I think it's now clear. So what are the different situations where you may consider the structure to be behaving non-linearly? Now let's plot a graph here. This is a displacement graph and this is the loading graph. So this is loading means the one inside this parenthesis. So if it is behaving linearly, then it would be a straight line. Okay. But if it is behaving non-linearly, then it won't follow the straight line. It may go somewhat like this, means anyway, but it's not straight. So I have taken one of the situation where it might take this path. Now, what are the different instances when you can say that when the structure is behaving non-linearly? So let's see few of the cases. most of the common cases. One is P delta, second is large displacement analysis. It is also known as geometric nonlinear analysis. Third is direct analysis. Now, this direct analysis is specifically mentioned in the AIC code. Fourth is also kind of similar to this P delta, which we also call it the imperfection analysis, where we have some initial imperfection. And then we have a very common situation like tension only or compression only member or support system. Okay, so these are few of the common situation where you may call the structure is behaving non-linearly. Another case you can consider it is like non-linear cable analysis. It's a kind of large displacement analysis, but specifically it is used for handling the complex cable analysis. So in all those cases, it's not necessary, but in most of the cases, you will come across the nonlinear behavior of the structure. So this is all about the linearity and nonlinearity. Apart from that, most of the structure behaves linearly. Okay, now I will take one of very simple circumstances where you can achieve this nonlinear state. Let's say tension only or compression only member or a support system. Okay, this is the structure. Okay, we will discuss on the structure. Now, before I go ahead discussing on the structure, let me first tell you that whenever you are doing this analysis in Staad, and there are few primary load cases like this and this, and also eventually you are doing some combinations, right, to find the envelope of all those loading action and finding which is the most critical one and designing against that. Now, whenever you are going to find the combined response, then you must be very much careful about taking the right method of combining those primary load cases. Now, I have seen that in many cases, many new STAAD users or maybe some of regular STAAD users are using the load combination method to combine the primary load cases. Obviously, we are going to combine the primary loading action, but instead, we can define this by directly using the load combination. Here you can see this is the load combination, right? We can use this load combination. Let's see what is the impact we are going to have in the structure if we use this conventional load combination approach. Okay, now before I dive into on the detailed analysis on stat, so just to let you know that in load combination, program is simply computing this one, not this one. Okay, please note this. Load combination simply uses this, left hand side expression to compute the final result. That means it will algebraically sum all the individual responses. So whatever we are getting from the primary load case response, program would simply pick them up, multiply with the factor that we have defined in the load combination, and then algebraically sum them up. So eventually, if your structure is behaving linearly, then it's not an issue because in the linear case, this one is going to be same as this one, right? For the linear case, it's fine. But if it is a non-linear case, then you are going to have some trouble. The reason being, program is going to deliver you this result, but in reality, in non-linear case, this value is not going to be same as this value. That means what we are going to get in the reality, in a real life scenario, both the loads are acting together. So we must want to get this result. This is the most realistic result, right? So this is the result when both the loads are acting together simultaneously. Just for the simplicity of calculation, we are adding up those individual responses to find the overall structural responses, combined responses. So in the linear case, as I mentioned, as this one is same as this, so we can use this approach to find the combined structural response. But if it is a nonlinear case, then if you are using this approach, you're not going to get this value, which is the most accurate one, exact one. So ultimately, you are getting some misleading structural result. That's the reason you should be very much careful while using this load combination method. So this load combination method is only allowed when the structure behaves linearly. Okay. Or else, if it is a nonlinear structure, then instead of this load combination, you should use another method of combining this loading action. We call this repeat load analysis. Now, in the repeat load, program would actually solve for this. It will create a load vector where both the individual loads are acting together, and program would find this one, which is the most exact and the real one. Okay, so let's see with a simple example to understand this analogy. So here we have taken this a simple kind of structural arrangement. It's kind of an isolated footing kind of thing, but it's not exactly the same footing. We have just created some of the arrangement to explain more clarity. So what we have done is we have um, put a hinge over here, and we have put some compression only spring support here. So you can see here, this is the compression only springs, and we have applied some values of those spring stiffness, okay, at these two. And we have applied the lateral load at the tip of this cantilever column with the magnitude of 20 kilonewton in one case, and in another case same value but acting in the opposite direction at the same point. And we are going to see what's structural response. So for I have already created the combination here, so let's run the analysis. Let's see the first one. LHS means acting from the left hand side, this one. Now, obviously, this support was assigned with a compression only support. That means the support can hold only the compression, so it won't restrict any kind of tension. But the moment it experiences compression, it will give the resistance. So here you can see this portion is freely moving upward, and this portion is getting some resistance. That's the reason you can see some kind of bending action here. The same thing can be verified from here because here we are applying the load from the left hand side. So this portion is going to experience some uplift, and as this is a compression only support, so there is no constraint. That's the reason this point can move upward freely. And that's the reason you can see here there is a zero support reactions. The support reaction is here only, and to maintain the equilibrium condition, this point has ultimately beared the opposite reactive forces. Okay, so remember this value 16 minus 16 and 0. Now same thing if we see for the other loading action where the value of the magnitude is same but acting in the opposite direction. You can see this portion can't hold this point, and obviously it is moving upward very much freely. And this portion is giving all the resistance because this time this is not experiencing the uplift, but it is experiencing the compression. Okay, now the reaction this time is 16 kilonewton and minus 16 to maintain the equilibrium, and this side is experiencing the zero reactive forces. Fine. Now the main interesting question come into the picture, where I have applied a combination case where both these two are acting together. Now you know that both the loads are having the same magnitude but acting in the opposite directions, but this time they're not acting at different instants. They're acting simultaneously at the same point of time. So by your intuition, no need to do any structural analysis or needn't have to be a structural engineer, but just from an intuition, you can guess out like this time this force and this force are canceling out each other, right? So there won't be any kind of reactive forces at these joints, these these support joints. But if I see the result, again the combination case, what could I see? You can see there's took a shape of an arch, which looks very much unnatural, very much unusual kind of this shape function. And if I see the reactions, you can see this portion also experiences 16 kilonewton, this portion also experiences 16 kilonewton, and this one is minus 32. So what program is doing here? Just recall this function expression that I have explained a bit earlier. Program is simply doing the algebraic summation. So here in the first condition it was 0, second condition it was 16, so 0 plus 16 it is 16. At the center in both the condition it was minus 16, so minus 32, and here on the previous condition it was 16 and second condition it was 0, so 0 plus 16 again 16. So essentially program has algebraically summed them up, the individual responses, and delivered you the structural result, which is very much misleading. Even if you see the deflection diagram, you can see it takes a arch-like shape moving upward. How it is going to happen? Because the loads are acting simultaneously at the same point of time at this point, having the same magnitude, and why this should take a shape of like this bending shape like this. So this is a misleading because we are using the load combination option. So now let's see what if I use the repeat load option here. So let's create a third primary load case, because repeat load basically is a new load case because program is going to solve for this rather than picking those individual responses and then algebraically sum them up. No, repeat load is not doing this. It is a separate load case which program actually solves by the stiffness matrix method. So that's the reason you are getting the exact result. So this is the repeat load, and let me drag these to individual load cases. And here you can see. Now let's perform this analysis. If I go to the post-processing mode, and this is for the load case number 4, which is the repeat load case. Now here you can see it is exactly what is expected from the structure. You can see the structure is still standing as its actual shape, actual position, because forces are being cancelled out. So that's the reason you can see the displacement is almost 0. And if I go to the reaction, you can see here for this one, it is 0. So which interprets, you can see at 0, which interprets that my nonlinear state of analysis are well captured if you are using the repeat load option instead of the load combination option. So that's the reason we strongly advise you to first identify the structural behavior by the virtue of the type of the analysis you are doing. Means if it is a P delta analysis, a direct analysis, large displacement analysis, or if there is any kind of tension only or compression only kind of specification, then you need to just understand that these kind of structure are classified as a nonlinear structure, and accordingly you need to use the repeat load instead of the load combination option. So hope you got to know the essence of this repeat load feature in Staad. I've seen several users, they straight away use the load combination, come back to us and just asking us why Staad is giving so much of unusual out of proportion result. But this is the main fact. They do the mistake, and they are using the design based on this erroneous and misleading result. So signing off today, and if you have any question, please drop your comment in the comment box. See you next time.